Okay. Thank you very much, Michael, for the introduction and for organizing all this meeting. And hello, everyone. My name is Deng, a lecturer from School of Computing at NU. And I'll be talking to you about some idealized CIS modeling and then data assimilation, looking into the multi-scale feature. And this is a collaborating work. It's actually a series of work with Professors Nan Chen, Sam Etchman, and Zhuhua Hu from University of Wisconsin-Madison. So this is the outline of my presentation. So first, I will skip this overview of the CIS models. So there are a series of models like the continuous models, and then there are some other particle models recently. I will be focusing on this multi-scale modeling based on these DEM particle models. So basically, discrete element model particle, like looking at the CIS flow modeling simulations, which is quite recent directions on the CIS modeling. So like for example, the works by Herman and Andy, recent works. So we started based on this DM model and then look into the Lagrange multiscale. We skip this part as well. And they majorly focus on coupling method, which is particle continuum model. And then I will present you some recent work, mathematical theoretical results. I apologize, there will be some formulas here. And then I will look into this data assimilation. So basically, based on this multi-scale coupling framework, we developed a Lagrangian O'Leary data assimilation tool, and then some summary and outlook. So we start with this, say we have some marginalized zone, take some images, and then using some idealized CS flows to approximate the ice particles or flows with some like larger flow cylinders. Basically here we are looking at all cylinders, and then using this second Newton's law to model each of the cylinders. So this model kind of captures like collision, ocean drag, and some features like right now it's in a very idealized setting. So we consider, for example, this displacement angular displacement just as simply as these equations, and then momentum, second Newton's law. We have the collision. Flow collision, and this is the drag force. This is quadratic drag law for the ocean. We can similarly have atmospheric drag force as well. So then this is an angular velocity equation, angular momentum equation, and then this is the ocean, simple ocean scenario setting. So this ocean is kind of simplified model for the shallow water equations. So based on theory work by, for example, Andy Maida in this direction, look into the largest, highest energy modes, and then give us very good approximation to the shallow water or quasi-geostrophic model. So we just take this model for the ocean current. So this whole idealize the setting, give us a suitable and very cheap, simple framework for testing some mathematical method ideas for data assimilation or multi-scale parameterizations. So based on this simple model in an even simpler setting, so assuming that the angular velocity is absent, so assuming no angular velocity, so we derived some theoretical results with Professor Har from Seoul National University recently. So what is looking at? So when we don't have angular velocity, and we assume that the ocean current is constant, like in constant ocean velocity. So given the particle flows with some initial velocity, random location, we can show that when time goes to infinity asymptotically, each particle, no matter if they have collision at the very beginning or not, so what's the initial velocity they have, as time goes to infinity, each particle velocities will go to this constant, will converge to this constant. So this is a very special case for the dynamics. And then on the particles, momentum energy for the total whole system. So again, assuming this angular velocity to be zero, we proved that for the particle displacement and velocities for the solution to the DM system, then we have this momentum energy overall behavior for the system class particles. For example, the first equation here shows that assuming there's no drag force, then the whole momentum, the total momentum of the system is conserved. So this is dm1. So m1 is defined as this one. So this m0 is the total mass of all the particles. And m1 is the total momentum, linear momentum. And then it is conserved if there's no ocean drag force. And then here on the right-hand side is a total ocean drag force for the angular momentum, which is that dragging the whole system. And then for the energy, so energy, we have two pieces, the linear angular momentum and then the energies due to the collision, linear elastic part. So we have the total energy to be displaced in the sense that if we say have this ocean drag force to be zero, then there's a lower bound for the energy. So this energy will be displacive, but there's still some energy left in the whole system as the time goes by. So this is some theoretical results from like kinetic theory type of analysis. We have a similar analog for the density function. So looking into the macroscopic behavior of these particles. So let F here be a density function. So we derive in the limit sense that when the number of the CIS particles goes to infinity, we have a Boltzmann type of equation looking like this. And then based on this equation, we derived also like the analog of the angular momentum kind of conservation. Well, not conservation because we have drag force here, and then the energy displacing behavior derived. So I quickly just show this very recent result. This is a still ongoing result. And then we look into the particle continuum multiscale modeling. So the key idea is that, so we have a flow model, so very ideas like setting. We have, say, this is some domain. We have a large number of flows sitting in the whole domain. And then the multiscale model, we kind of first decompose the domain into several pieces, say domain decomposition. So we look into each cell, like say this is core cell. The core cell contains some number of flows, and then we have some mesh. Each of the cell there's a small dm. So at the end of the day, we have a coupling system where in the local element, like each of the cell, we have one particle model, one DM model. Globally, we have this this Eulerian type of information, meaning that in each cell we have some average information, say average like angular momentum, average the linear momentum information, and then we try to couple them. So this two direction, two models in this sense. So Eulerian domain decomposition, larger scale, looking at the continuum model. And the fine scale model, which is Lagrangian particle model in each cell. So looking at scale, small scale, and this can be fully parallelized. So basically in each DM, we are using, say in this case, we're using a simple periodic, double periodic boundary conditions, meaning that this DM, once we have flow, which is leaving this cell and then go back to this one. So in the computational setting, so we have this flow to going back to this cell. So we don't need to have this communication done at this level of this DM model. where the communication will be done through the the continuum model, the Eulerian grid. So this is done where this Boltzmann description with this flow distribution function. So going to a little bit more details. So distribution of flow size, thickness, and then we write into some density function F. And then look into the momentum distribution, say take integration with the ice velocities, we get the average, like local average, the mean velocity, like this one. So we go through the process and then we end up with some Boltzmann type of equation with respect to all the dimensions that we want to characterize in this model. Where on the right-hand side is trying to capture the collision type of force. So the model development, this is a diagram where we start with, again, the CIS particle model, say large number model particles, flows, and then look in the Boltzmann description, Eulerian grid, continuum model, so equation of moments, and then the local models, which is the fine scale, fully parallel, and using this DM model, and then we couple them. So this is a little bit more details on the development. So particle model, again, looking at the distribution, and then Boltzmann description during the integration. We end up with equation like this. And then from here, we do integration again, substitute the particular, like say for G to be some mass, we get the mass conservation. For G to be like the momentum or velocity, we get the continuum equation for the linear momentum or velocity. Similarly for the angular momentum, angular velocity. So we have a coupled system. So particle model, again, the particle model we have for the fine scale. And then the larger scale, the coarse scale, we use this continuum model based on the conservation laws here derived from this Boltzmann type of equation after integration. So the coupling process is we take a very simple first step. So we feed the particle flow data information. So basically look into each cell. So we do some averages on the flow particles and then statistics moments, and then feed into the right-hand side of this continuum model. So here in the right-hand side, we have the angle bracket to showing the averages on each cell of like the drag forces or drag torques. And then that's from the particle model feed to the coarse scale continuum model, and on the other direction, so we solve this continuum model. We adjust the flow physical quantities on the particle model on each one. So this is for the purpose also the parallel computing. So we do the parallelization at the level of the continuum. And then again, so this is the overall coupling procedure. So we feed it two directions. So this is quite a simple framework. We did some simulations like with this about 41,000 flows. This is a scenario like flows smashing, like colliding to some coast. And then we observe that look into the L2 like kind of error quantification, meaning that here in the sense that we have a multiscale model. We have this coupled model, the continuum coupled model, and we have the original system, which is the original particle model. So we compare these two models, two equations, the solutions, looking to the L2 norms on the like CS concentration in this case. So the CS concentration is well captured, meaning that the multiscale model using this framework, the Boltzmann, and then do the integrations, can capture the L2 norm of the CS concentrations in a linear rate. With respect to say this the mesh size, which is like how coarse is our mesh, and we have basically a good match of the multiscale model to the original system, where the computational wise roughly reduced about 10 times. So in the parallel setting. So that's a very quick introduction to the framework, multiscale framework. And then based on that, we look into the data assimilation. So what is going on here? So we went to, we basically need two data assimilation tools. One is for the particle, another one is for the Eulerian equation. So for the large scale features, the Eulerian parts, we use the continuum dynamics with Eulerian observations. We observe the statistic quantities, say in each cell, we have, say, observe some averaged informations. While in the Lagrangian data assimilation, we have some, say, in some of the cells, not all the cells, we can observe some of the particles. We have some particle, like some drift information to collect some particle information. And then the coupling is going through using a model we call the conditional Gaussian, so which has this closed analytic formula. So I will in my next slide, so we show what is the conditional Gaussian method for this data assimilation. So this is the tool. So data assimilation tool, conditional Gaussian nonlinear filtering. So for both systems, Eulerian or Lagrangian systems, we can write them into vectorized system. So the first one is that say we have this Z. This is the observed information. So and the U contains, for example, in this case, we say the data assimilation goal is to recover better the ocean mode or ocean currents. So this U in the second equation is here is that the information we want to recover, where Z is the observed Lagrangian flow tracer data. So you say in both Lagrangian setting or Eulerian setting, this Z has contained some observed data. For the Eulerian case, we have the coarse grade. We need the observed data for all the cell grade. Where for the Lagrangian set, we only observe like partial of the particles, not all of the particle information. So this framework, this data assimilation frame has a closed analytic solution. So for the conditional mean and the covariance, so this is given by this work, recent work. So we adopted this data assimilation tool. And then here it's to show that the data assimilation skill scores, we look into the typical things, which is the root mean square errors and then pattern correlations, and then uncertainty information gain, like uncertainty reduction defined by this entropy, relative entropy. So we look into these ones. These are some results showing that how the Lagrangian data, DA works for the ocean recovery. So what is going on here? We consider some simple setting with some number of flows in some idealized setting with some domain, here's some domain, and then say this L in this case is number of particles. Say we have, this is a 30 particles. This beta here shows us the ocean drag coefficients. Like we have from small drag coefficients, 0.1 to some larger ones, and then to look into how this data assimilation works on different scenarios. And then roughly we observe that as the number of particle flows increases, like from say 20 to 100 over, then the root mean square decreases. And for all the scenarios of this ocean drag forces. So if the ocean drag coefficients is large, then meaning that the flows will go to more like asymptotic regime earlier than based on the theory understanding showed earlier. And then the pattern correlation, similarly, that's when the number of particle flows, pattern correlation will go, and the scores will go better, meaning go to 1. The closer to 1, meaning the better the method is. So this is uncertainty reduction. Similar behavior we observed. This is ocean field recovered at time t equals 8 with some non-dimensionalized time. So overall, we have this Lagrangian data assimilation on each cell performing well if we have a sufficient number of observed particles with like 10 or 20, for example. In this case, like 20 flows, the pattern correlation is around like 0.6, where in this case is a little bit smaller. So it's a robust to model parameters such as like drag coefficients in this case. Now, this is a case for the Eulerian data assimilation. Now it's on the Eulerian grade and the coarse grade. So we look into also the pattern correlation and root mean square errors. So we observe the similar behaviors as the number of particles increases. The overall pattern correlation increases, like say this in this case, approaches 0.7. So there's a limit. So this limit, meaning that the pattern correlation do not go better when we increase the number of particles. The reason is that, say we have a fully packed domain, a domain with fully packed flows, then meaning that the flows will barely move around in the domain. And then that will not be able to recover the ocean current. So that's expected. And similarly, we also look into the concentrations. Say, with respect to concentration, the pattern correlations will decrease if the domain is more, the domain is more and more packed with flow particles. So concentration goes higher, then we have a more packed domain, and then the data assimilation scores will decrease, as I just briefly mentioned from this figure. So those ones are in different scenarios. Say a fixed grid number. So this is with respect to the Eulerian size. So when we increase the grid number size, the pattern correlation increases. Where we want to say, notice that in this case, even we have a very small, very coarse grid, say this is 6 by 6, the pattern correlation is already 0.85. So meaning that in this setting, in this very idealized setting, we don't even need a fine grid to capture the large behaviors of the flow dynamics. So in the coupled setting, so the coupled data assimilation setting, so say this is some truth ocean field. And then if we only apply the large scale model, large scale data assimilation, we observe that the ocean current won't be able to fully recovered. Only in the case when we using the small scale Lagrangian data assimilation to capture local features, so we can recover the energies, the ocean mode. So this is what we are showing here. So the pattern correlations in the case of only using the large scale model for the only using the Eulerian data assimilation. And then this is the case when we combine with both. So the results has been improved with the coupled feature. Again, this is a super idealized setting, not like really into a more like realistic setting. So I will give a brief summary. So I introduced a framework starting with the particle model and then go to the continuous, and then develop a multi-scale model. And based on this multi-scale model for the CIS particles, we develop a Lambda tool, which is a data assimilation tool for the purpose of recover to understand more the ocean or atmospheric mode. So I didn't show atmospheric mode recovery, but we can do that in theoretically. So there are some other ongoing works, for example, IceNet, recent machine learning assisted CS modeling by Anderson, like look into the satellite images and then tend to detect recovery. So following ideas like this, so recently we have some other works in a similar line, which is look into the graph neural network for flow recovery, like flow dynamics. Then the data assimilation we are trying to apply these data assimilation tools for a more like realistic setting. So we are recently collaborating with Andy Keys from NEU, look into the Cosmos data and then to see if the data assimilation framework can actually how good it performs in the more realistic setting. So I will stop here. Thank you very much.
All right, thank you very much. Just unmute myself. Yeah, that was great. And thank you for giving me so perfectly the time. Do you have some questions?
I'm happy to ask a first question if no one else wants to.
Yeah, sounds great.
Hey, Quanling. Nice to talk. Good to see you again. Regarding the model that you developed in the first half, can you identify a rheology for the continuum model from your multi-scale approach? So what I'm thinking here is about the rheologies proposed by Haley Shen and Danny Felton for the marginalized zone, which I don't think have ever had any numerical or experimental backing. And then there's the sort of more recent idea that the marginalized zone is just free drift, so that the internal stresses are zero. Would you be able to provide some numerical evidence to go along with those ideas?
That's a good question. Yeah, thank you. I think following this framework, if it's free drift, then I think this numeric simulation is I think it's not really difficult. I mean, I'm doing very idealized the setting, but in realistic, maybe using realistic data, maybe it's much harder. And then the rheology from this model, I don't have a very clear idea how it looks like in this continuum part. And then it's not very clear.
The thing that made me think about it is that you've got collisions in the model, and that's what Haley Shen's rheology is based on. If you don't know the literature, then just reach out, and I'm happy to send you the papers that I'm referring to. Anyway, nice talk. Thank you.
Thank you.
I'm just going to ask a question if somebody else wants to ask one. Just, it wasn't clear to me why you had this shallow water equation for the fluid. Like, what was
that's
because what's the forcing is just a current, is that right? Like,
yes, the forcing is like the drag force, ocean drag force, the ocean current, right? This last equation here, this is a linear stochastic model for the ocean mode. Say what we can do is that I did the simulation as well, even though this has been verified in these papers, for example, by Andy Maida in 2016. Or he has a postdoc, DG, worked on this verification as well for the quasi-geostrophic model. What they did is that, okay, they do the simulation in the stochastic, for the stochastic quasi-geostrophic model or the shallow water equation. They look into the ocean mode, like in the physical domain, solving these equations, and then transform it into the free mode. And then all this mode, they using the statistical method to characterize the coefficients.
But your model's taking that as input. It's not simulating that shallow water geostrophic flow. Is that right? Or the
yes,
ocean current's an input.
Yeah, it's input. Say this is given. It's given information. We only have one way information, meaning that the ocean current only impact the CS flows, not the
Yeah.
not the other direction.